have with us Dr. Ockley. He's the Associate Director of MSRI, which is the Mathematical Sciences Research Institute. And when he's not at MSRI, he is a geometer on the faculty at Kansas State. So without further ado, let's do some math.
I have some warm-up problems for us to begin with. Can you hear me? It's been a while since I've been in the big lecture hall. You got to say, yo, pinhead, shout if you can. So, start things off. Draw a picture of the cube. These are actually warm-up. I want you to think a little bit about a couple warm-up problems. So, first question is, how many square base pyramids So by this, I want you to fill the cube with these pyramids so that their interiors are disjoint, and I want the smallest number possible. Sure, you might be able to do it with 533,286. But what's the smallest number of pyramids you can do it with? The second question, we'll stick on the second board, is going to be, what is the relationship between areas of these semicircles? So I have one there, one here. The pink doesn't look very pink-like. It works better than this one. And so, start. Do you have an answer or a question? Which one do you have an answer for? For the second one. So I want to get, so that I have several people have answers, I want to give you time to think about these guys. So right angle to what's the area? So, while you're thinking about that, let me ask some questions to try to get some background on you. How many people here know the formula for the area of a circle? All right. How many people know why the area of a circle is what it is? I have a few. Well, how many people know the formula for the volume of the sphere? How many people know why the volume of the sphere is what it is? You know, small surface area of the sphere. All right, and why? All right, so we're getting a few. We'll get there. In fact, we're going to talk about how you measure the size of different things and why it is what it is. And then we're going to see just some crazy applications of this to how your mom might decorate a couch, so there you go, or the shape of the universe, or what rock crystals look like, or how a plane flies. All the applications might take place in the last 5 minutes. If you really want to understand those applications, we need to do a couple more Saturday morning math. So what was your name? Logan. So Logan had the answer to problem number 2. Did anyone else have an answer to number 2? Aha, so we're getting a few answers here. Does anybody have an answer to number 1 yet? Couple. All right. So what's your name? Hannah. What's your Anna? Anna. Sorry. So what's your answer to number 1? 6. So we have a 6. Hey, bit. We have a 6. Can you explain how we have 6? So 6 is possible. So, or maybe 6 is possible. You want to run up front and show us 6 or describe 6 to us? All the points in the middle. Can you draw a picture? What's your name? Michael. Are you understanding what Anna's saying? You are. Tell it to us. So Anna's saying put a point in the center of the cube. Michael's saying that, hey, I understand it in the way to see if you understand it, as Kenny says it. Then from each face, go up to the corner of that. So we have a pyramid that looks like this. We have a pyramid that looks like this. A pyramid that, from the bottom, from the front, from the right side, from the left side, from the top. Can we do better? That's 6 pyramids. We wanted the smallest number. Yes?
Is there any limit to how big the pyramids can be?
Well, they certainly can't have more volume than the cube.
Okay.
I mean, it's a good question, right? It's a good starting point.
So do we just make it like one big each square pyramid, not be able to put any others?
Well, if you put one big square pyramid, where do you put the point? I think you're going to miss spots, right? I mean, I have the bottom be one face, and then I put a point over here. Am I going to have anything over there or at that point? So we can think about this. So as you're coming in, I can ask you, what's your name? Hey, you, late people. Who are you? Aaron and Eva. So we're trying to cut a pyramid into a cube, the smallest number of pyramids possible. We're trying to figure out why we might do this. So maybe to motivate this a little bit, let's take a different question and look at the answer. If I take just a square, unit length, cubit by a cubit, I can cut that into 2 triangles. Looks like this. When I do that, this, we see a way to do it before. So what's your name? Jonathan. And so Jonathan, how do you cut it into 4?
Well, you have one pyramid whose base is the boss base. And you put its point at the upper left corner. No, to the left.
Upper. That was.
Well, it doesn't actually matter.
But doesn't matter.
Yeah.
So was this one you were thinking of?
Yeah.
Okay.
And then you put another pyramid on whose base is at the top, and whose point is at the lower right corner. And then you're missing a bit if you put one in the front, going to the lower right corner.
But if I did that, if you were putting the corner here is where you were putting it. So I'm filling up this triangle with the pyramid on the bottom. And then if I understood,
Sorry.
square on the
The
top,
right face.
The right face. And then
Going to the upper left.
to collide with one of the other pyramids that are coming down. I like it, but so we're definitely not convinced that 6 is the smallest number here. Yeah?
Why was it, because my drawing was described like, what it would be taking up on the faces?
Yeah, I can try describing that. Using color.
Just the experiment, like, one face, and then after the face.
Saying, I think you were saying start with the triangle here, let's go across here, and this would connect down to that corner, this would connect through like this.
Yeah, that would be 3.
I would be 3, we have a 3. I think I kind of like that. So, can you describe, clarify a little bit, why 3? So wait, time. I'm not going to let you say that. So I think you're getting ahead of us, but you're moving on to something. So, am I drawing the picture that you, what's your name? What? Catherine. So shall I continue drawing here? So, I think when we have this 3, what I want to do is actually get to it in a different way, if I may. Just to try to illustrate. And I also want to try to pause for a point. So, it's almost a little unsettling to say, wait, shouldn't you be drawing this when I step over here? I'm going to step over here. When we started talking about the sizes of things, here, if I've got a triangle of side length 1 and height 1, and the right triangle, what's the area of that triangle? Anybody or everybody? Area of a triangle?
1/2.
Half base times the height. And certainly, if it's square, and you've got the side of 1 and the side of 1, this triangle is the same as this triangle. There's a rotation right through that diagonal, and you can put 2 of them in, so it has to be half of the total of 1. What happens if this is a B? Well, if I stretch this by a factor of 2, the area gets bigger by a factor of 2. If I stretch it by a factor of B, it gets bigger by a factor of 2. If I stretch it this way, it gets bigger by a factor. So I can think about what happens when I scale the length and the height.
You know, it's bigger by a factor of B squared.
If I just stretch one distance by B, so if I have this, B coming across here, and 1 here. It's important that there's 2 different directions. If I stretch everything by B, then indeed it would get bigger by B squared. So this picture tells you that the area of a triangle is 1/2 the base times the height. Well, at least that's the area of a right triangle. What happens if the area is not a right triangle? Well, it's like the area that you see on the side of this deck of cards. Compare this area to this area. I'm not exactly a professional mathematician, but I can at least slant cards from here to here. This is the best magic trick cards for the day, yeah? How do those areas compare? They're the same, because I have the same number of cards, the same number of slices. So I could do the same trick here with a square and with a triangle and just slide it over that way, and it still has the same area. And so, we're talking about sizes of things. I'm probably going to get to the volume of a pyramid, which is why it's not Jonathan. In fact, something before jumping to 3, we got a very quick and correct answer there, is how could you discover this if you had not seen the 3 in your mind? Is there's a nice trick to use in geometry where you deform things and you take a look at degenerate cases. This is the picture you have when you put the point in the center of the cube. If we're trying to get rid of pyramids, let's instead of making the pyramid disappear, let's make it get smaller, and smaller and smaller and smaller, and then disappear. So if I take this point and I start pushing it upward in that direction, then this top pyramid shrinks and gets smaller until I have a pyramid coming from the bottom and then one from each of the sides, and there's nothing from the top end. So that's how we can get to 5. Does that argument make sense? And if I can push from the center where I got 6 up to the top where I get 5, if I wanted to get 4, where do you think I should push the point of the center to? Somebody said an edge, right? Because if I push it towards an edge, I can just pick a pyramid. I pick this pyramid on the right-hand side, and I can make it get smaller by pushing the point this way. It gets smaller and smaller and smaller, and then poof, it disappears. That type of degeneration is a nice type of mathematical argument. So, and then I can redraw the picture. And then from there, well, if an edge gives you 4, then, so center, base, edge, then we'll have vertex. So let's try to draw it with the vertex. Maybe this got messy enough that we'll redraw. So let's make that point the point on the far back, and then I can make the bottom of the cube as a square, which will be our base. And then it runs up here, 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 here. So there's one pyramid that I hope you can see. Now we take the front, and from the front base, go back. And we should see another pyramid. That's the 4 lines. And if we take the right-hand side, then we have another pyramid colored in white and clear, already colored. And I claim that if you do this with the cube, these are all going to be the same size. In fact, I happen to have my handy-dandy portable TSA-approved cube. So, and it happens to have a blue, a green, and a yellow pyramid with this base that you see here. And how can you compare the sizes of the blue, the orange, and the clear pyramids? They're the same. Can you see the motion that takes one to the other? If you look through this point of the cube, you see that it's got a line here, a line here, a line here, 3 lines. They're all evenly spaced. It's a cube. I can rotate this to make the green move to where the blue was, and the yellow turn to where the green was, making, you see that hopefully the green pyramid is exactly the same size as the yellow pyramid, is exactly the same size as the blue pyramid. Since each one of these things is the same size, what, my friends, is the volume of a pyramid? One-third times, and then if this is a 1, 1, 1, it would just be 1/3, but I can stretch this out to be a length, a width, and a height. And so it would be 1/3 times the width times the length times the height. The width times the length is area of the base times the height. we have questions on that, or why that formula might be? It's more than just knowing the formula, it's knowing why the formula is what it is and being able to explain it. Higher dimensional animals try the same thing. Circle. If a circle has a diameter of 1, what is the circumference? I don't know. Let's call it some number. Measure it. We'll just call it pi. But as soon as you do that, the same sort of scaling argument that we did with the triangle that was 1 by 1 would say that if the circle had a diameter d, what would the circumference be? So if you make this distance twice as big than any other, and you make all distances twice as big, all distances get twice as big. If I make it d times bigger, this would be pi times d. If I describe the diameter in terms of the radius, how many radii fit inside the diameter? And so that makes this circumference equal to 2 times pi times the radius, because this 2r is that d. So that's a formula for the circumference. It's not so bad. What about the area? So, one of the points about coming to a math circle is to meet mathematicians. It's kind of like going to the zoo, right? It's not exactly the same kind of creature. You get somebody or something that's different here. And so, I'll get a couple more. So, my house, honey, where's the phone book? Phone book? Right? The conversations might be a little different than you might see in other households. But phone book makes a pretty nice circle. It actually looks something like this, right? A little uncoordinated, which is something else that you might learn about some mathematician, right? But, you can imagine that if it was actually coordinated, this thing would look like a circle. And then I could take this thing and I could open it up, right? So let's do some carnage to these things. Let's see some blood and guts here. So if we want some blood and guts, let's take a pair of scissors like this. Let's just cut this from the top straight down, like this. Maybe I'll draw this radius here on green. So after I cut that, then let's take a hand here. Let's take another hand here. And pull it open. When we pull this open, what we're going to see is the circumference lies flat on the table. You cut it down to this point here, so it'll have a height coming up to here. And then it will have red rough sides that look like that and look like that. Exactly like taking the phone book here and holding it like this. This is half of the circle and it doesn't quite go into the center, but we could send it into the center. And then unfolding it so that it looks like this. Yes? A few of you have these phone books. I'll pass some more phone books out so more people can play with it. Take it from here over here. So what is this shape going to be? Is this edge some funky curve? What is that red line? How should I draw that? somebody say a triangle? What's your name? Michael. Say it's triangle. Why is it a triangle? So this one is smaller and this one's bigger, so it kind of, that makes it smaller up here at the inside. It's going to be close to 0. How exactly is it exactly triangular shape? Well, if I move one thumb distance down this way, I get some distance coming across like this. That's moving one thumb and doing one distance. What happens? Maybe I should draw that over on this side. What happens if I do 2 thumb distances? If I do 2 thumb distances, I get a line that looks like that. 2 thumb distances go to here. What happens when I go out 2 thumb distances to the length of this arc compared to the length of that yellow arc? How does the length of the orange arc compare to it doubles, yes. That's that scaling argument that we used when we decided that the circumference of the circle was pi times d. So we're still just using the circumference back. And so that means that this distance is twice this distance. If I triple it, it'll get 3 times as big. It means it's proportional, and that's the definition of making this thing a straight line. That's why this really is a straight line. Aha! So this, maybe I should draw it in blue, is a triangle, yes? It's my magic trick, right? Here it is, deck of cards. You do this. How does the area of this compare to the area of this? How does the area of that circle compare to the area of this triangle? Aha! So, what is the height of this triangle? That's the radius r that we drew in green over here. And what is the distance when I take this thing and take the other half and I open it up? What is this blue distance? That's the whole circumference. Sure. And so what is the area of our circle? It's the area of this triangle, which is 1/2 the base, which is c, times r, which is 1/2 times 2 pi times r, and more carnage, death and destruction, we kill the 2's. There go the 2's. And so this is why the area of a circle is pi r squared. I've got more phone book deliveries to make. You can play with those, pass them around. So, we already did use volume. If I had the volume of a box, if this part has an area capital B, and this is a height h, what is this volume going to be? What? BH. Yes? Because if this thing cuts up into B little cubes, B little squares this way, and I have H levels, I get B little cubes on this slice, B more, so B plus B plus B, B times H, yes? Now, if this was my beanbag cube, and I could take this thing and squash it around this way and this way, it was made with all those little styrofoam pellets, would it matter if I had the volume of something that looked like this? If this has an area B up here and has a height here, what's the volume of it? Right? It's still BH just because you can take things and squish them around a little bit without changing the area, just like the deck of cards. It's the same magic trick. So in particular, you can tell me what is the volume of a cylinder. And in this case, what is B if this has radius R and this has H? So this would be pi r squared, the area of the circle, times the height. I'm going to fill up and have a whole bunch of volume formulas. People in the back of the room just have to be doomed unless you've got Superman keepers, because you're probably not going to see my board work at that distance. What about the volume of a cone? Actually, I'll draw my cone in a slightly different way. I think that's the way I want to draw it. So, right, we've got this pyramid, has a square base, and the volume is a third the area of the base times the height. So what's the volume of a cone going to be? It's still going to be a volume of a third times the base times area of the base times the height, because I can make first my square pyramid. I can imagine little bamboo struts coming down from the top, and then I can push on those bamboo struts with my little beanbag pellets in it, shifting the shape at each level. I still have the same number of beanbag pellets, and so it's going to still be 1/3. What is the area if this is R? That's H. What's the area of that circle? So what's the area of the base? Yeah? You indicating something in the base vector? Yeah, you turned your head. Is that a wave in a hand or no? Mike? Yeah. Right? We're now getting to the point where, okay, yeah, I can kind of see where this is going. So now you can also tell me the volume of a sphere, right? Maybe not quite yet. So, we have a second warm-up problem. So, does somebody see the relationship between the areas of these three semicircles? Yes?
The area of the blue and the yellow semicircle to the area.
Sure. What's your name? Justine. Sweet. Sweet Justine tells us that the area of the clear labeling these things in a way. The area of the A turtle plus the area of the B turtle equals the area of the C turtle. Yes? And so, why is this true? It's the same beanbag and scaling arguments. If you put a square here, and a square here, and a square here, you know that A squared plus B squared equals C squared. That's Pythagorean Theorem, which you can prove by drawing lines through the squares and then doing this kind of slide motions to move the pieces of these two squares to fill in this square. It's a good exercise to do. But if that works for squares, it would work if I stretched the side of each square by a factor of 2 and did it with rectangles that were 1/2 in ratio, or 1/6.37, or any ratio rectangles you'd want. Or it's going to work with any other similar shapes you stick on the sides of a triangle, because once I can do it with rectangles, I can just do the beanbag shift around motion and get this area plus this area equals this area, which is maybe a much nicer way to describe Pythagorean theorem. It's talking about areas that you suspend across the right triangle. Yes? fig trees. There's one, nothing. Yeah. So when I draw this, let's make this have a radius r. In fact, this thing is going to be a sphere, so all those radii is r's. In fact, we're all non-mutants in this room have a couple of spheres here. Here's my 1 cubit sphere. What's the definition of a sphere? Yes?
Perfectly circular and round, solid 3D shape.
Perfectly circular and round. Does the room have a garbage can? This is not a very good. There's a better one. So actually, if I took this thing and pushed it like this, it starts to get taller and then it gets smaller. So, dancing bears. So, can I get a volunteer to walk on this thing? More carnage, right? But if we sit here and we roll this thing this way, the height here is the same as the height here, is the same as the height here. Does that make this thing turn into a circle? Perfectly round because the heights are all the same when they do that? I got a yes and I got a no. Fight. Dad. So. So this thing's certainly not a sphere, but if we're just talking about is this a circle to do the two-dimensional thing, talking about perfectly round, is perfectly round meaning it's got the same distance on the top and bottom of each side. In fact, that's not quite the definition of a sphere, is saying that it has the same distance from the bottom to the top of each case. This came, unfortunately, very obvious in the Challenger disaster. Because when they were testing the fuel tanks for the Challenger, they wanted to know that the O-ring would fit perfectly on the fuel tank, so they wanted to know that it was round. And the way they tested to see is it round is they measured the distance across here, the distance across here, the distance across here, and they said, yeah, those are all the same, therefore it's round, therefore the O-ring fits, and whoops. Turns out that the dad who said no, just because all of those distances are the same, it makes it a circle. No, it does not. You can have homologous shapes. That's an interesting puzzle. Try to find a shape where all of those distances are the same, but it's not a circle. So I want a definition of a sphere, and we've got to be careful here. Ooh. Yes? So it's a set of all points that are equidistant from a fixed point. In fact, this is what you have to do when they now retest the fuel cans on the shuttles out. And you've got your elbow, and I can fix my elbow and move my fist, and that gives me a perfect sphere. And that's the definition of a sphere. So all these radii are the same. In fact, I'll set this up so that this will also be R. Maybe I'll call this capital R, call this capital R, capital R, capital R. And this will be capital R. I'll make this height capital R. So now I can stick a right triangle in here. That looks a little bit like that right triangle over there. And if I take a look at this section, section of the sphere, if I get my samurai sword to do more cartage height, cut all of these things across like this thing, what I get is I get a spherical section coming in here, or a circular section. Maybe let's just take half of that section. So let's use a samurai sword or machete in this direction. Let's use a meat cleaver in this direction. And I would get some semicircular slice that would sit like that. Which I can take that slice and I can rotate it up so that it would be a semicircle with radius sitting right on that side of that triangle. Over here, I would get a slice that, oh, I drew that in the wrong color. That's supposed to be yellow. Over here, I'd get a slice that looked like this. Now there's an interesting puzzle. I didn't label this. Let's make the height of this guy capital R as well. So if this height is capital R, if I look at this distance little r versus this distance, and I compare these two to these two distances are the same. So what can we say about this distance and this distance? Because I'm just scaling it. I just take this and I multiply it by 2 or 2.78, whatever it takes. And so that means that this half of the circle would be the same. I could flip it up and have a half of the circle that would look like this. Or I could have a half of the circle that would look like that. And these circles have exactly the same size. And here we just slice this through. So here I've got this thing, and we just go slice straight on through. And take the meat cleaver in the other direction. And I get this thing, which I can rotate up. Yes? Now, how does this distance from here to here compare to this distance from here to here? What's the definition of a sphere? We don't want to have any explosions in space.
The definition is that it's from the center of the sphere, all these sides are the same.
All those distances are the same. So if I'm setting this distance to be the radius of this hemisphere, to be this distance is the same as this distance. So this distance here is exactly the same as this distance here. Or maybe said better, this distance here is the same as that distance there. So I can take this circle, put it on this side of this triangle. I could put this circle on this side of this triangle, and I have this half of a circle on this side of this triangle. And we just said the area of A turtle plus B turtle equals C turtle. The area of the yellow circle plus the blue circle equals the area of the pink circle. So if my sword, I take two swords, like the white witch, and go slice and get slices of bread, making these have slight thickness, the volume of this slice, the volume of this slice, and the volume of this slice, what's the relationship between those? And if I add it up for all slices of bread, what's the relationship between the volume of this thing, the volume of this thing, and the volume of that thing? The yellow plus the blue equals the red. Sure. This volume plus this volume equals this volume. But now we can plug these in. The volume of the cylinder of radius r and height r is it's got area and it's got height, and you take it in slices. Each one of these slices has the same. So it's going to be area of the base times the height, and the area of the base and the height. So what's the area of the base here? Louder! I can't hear you. Speak louder, pinheads. Pi r squared, that's the area of the base, times what's the height? R. Yeah. Speak louder, pinhead. That gets us going. So now, what's the volume of a cone? 1/3 pi r squared. A third the area of the base times the height, which is r, equals, and then the volume of half a sphere, oh wait, not equals, plus. And then, I don't know the volume of a hemisphere, but maybe I do. This plus 1/3 of this stuff equals 1 of this stuff. What plus 1/3 of something equals 1 of that thing? So that's half of the sphere. So, looks to me like we're up to the point where we now know the volume of the sphere. And hopefully you know why the volume of the sphere is what it is. So this is 2 half spheres, the same by rotation. So what's the volume of the sphere? R squared R, which is R times R times R cubed. Sure. So far so good? Still awake? You don't need to get up and dance yet. Can anybody guess how we might find the surface area of a sphere? Any guesses? Of course, what we have to do is more blood and guts, right? So here's the head of our alien, and we get out the Black and Decker. Straight into the center of the sphere, we drill a hole. And that's going to start getting bloody. Then we reach our hands into it, we go, and we rip the head off. Or maybe if you don't quite like that, do you ever have a field day where you've gotten a parachute, and you grab the parachute, everybody runs into the inside, you make a great big ball, and then you all run out and pull it flat. Or we can do that in gravity, we can do it upside down, climbing across the roof. Take the thing and go, whoop, whoop, right? We're going to take this thing, and just like we did with phone books and circles, cutting and ripping open, we're going to stick our hands here in the sphere. We're going to go rip, and we're going to get some shape. We'll have some blob here. It'll have some sides. It'll probably go up to just about the height that you see here. What do you think this shape is going to look like? Yeah, louder? A cone. Who said that? What's your name? be a cone. So just like with the triangle, we needed to argue that as a cone by looking at what happens to the circumference of the concentric slices. Here, it would be a good idea to argue that this thing really is a cone by looking at how the surface area would scale, to thinking about how the area of the various slices would scale, and then how the diameter would scale, to make sure that this scales in a proportional way. And so if this is really a cone, when you think through that scaling argument, then you're ready to compute the volume of this thing is equal to the volume of this thing. And what is the volume of a cone? So this is going to be 1/3 times the area of the base, which is the surface area of our sphere, times the height. Well, what's the height? That's going to be times r. And that has to equal the volume of a sphere. But we figured out the volume of a sphere right here, 4/3 pi r squared r. So what is the volume over here? Exactly copy that, 4/3 pi r squared r. Well, now we can just kill things in order to get the solution. So I see an r on the end, so what do? Kill it. Kill it. I see a 4/3 and a 1/3. I can kill it, and I can kill it. And so we're left with the surface area of the sphere is 4 pi r squared. Yes?
Yeah.
All right. Enough sitting around. We're probably ready for a break. But maybe, shall we do two things at once? Break and dance? Actually, are you up for a little more that I can show you and then you can play with it and break? Or do you want to immediately break?
Play with it and break.
Yeah, speak louder.
Break. Plus 3 volts.
Ego's too big for
I have 6 volunteers up here on stage. You'll be the first 6 to break.
Just a microphone.
Come on up.
I like to go.
Barely powered.
Oh, Jonathan.
Silly Jonathan, you make me. Silly Jonathan, you make me wait longer to eat. I will kill you.
Oh, you rascal, Jonathan. You're a tyrant.
This guy is withholding food. I'm better than
Top on top, bottom on bottom. Top on top. You, sir, would you stand in the center? Or actually, just stand closer, you can reach the center. So, I want left and right are straight. Hold these and hold it up. And separate.
which I'm shooting. ever so the distance between a line is back. It's not
Don't worry, we've got
I bet it does. Two cameras recording. Hi, internet.
No, it's reviewed by you. Yes, it's a triangle.
So, let's collect some data for you. So for collecting data here, how many volunteers get formed row so far?
Yes, like cross stage.
How many volunteers did I ask for? 6. So how many vertices do we have? You agree with that? So here we've got V is 6. How many faces does this thing have? It looks like this. 4 faces. I'm hearing 6. I'm counting triangles from the top. I count 1, 2, 3, 4. And then triangles on the bottom. Have 8 faces. How many edges does this thing have? We've got 4 on top, 4 on the bottom, 4 around the middle. We've got 12. The name of this thing is an octahedron. Now, in fact, we can do a dance. I can explain that we can dance 5 different shapes here. The first thing to do is maybe have somebody like this separate 2 hands there. So if you separated the blue lines, what do you think you're going to do? Yep. Now, this is a trick question. They've already separated blue. They want to get things so that it's as symmetrical as possible. If you separate blue everywhere and never separate green, you might have trouble. But if you separate the green, if you've got a green and a blue, then would we ever separate red? So what should you separate? Separate red. Let's keep top on top and bottom on bottom. Make sure which one is top. This is top. This one's top. Use 2 hands here. The other hand down here. And you have left and right consistent. And you separate that. Aha! So 6 volunteers, no mutants. How many hands each volunteer? 12 hands each volunteer. Dad, maybe in your family. How many hands each volunteer? How many vertex? 6 volunteers, 2 hands each. We've got 12 vertices. Oh, green has been split? Ah. Oh.
I have no idea what this is. They're all family.
Cool. So 12 vertices. Let's count the number of faces. And so, there's a lot. But non-mutants actually have this here. The people in the audience have the same shape. You've got 2 hands, right? Your hands have fingers with red vertices on them in the thumb and a finger here. And I can run here. The other hand does that same thing. And so, dot, 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 dot. Pass the joy around. We can get more volunteers here standing up. You want to draw on your friends? So, with this, we can interlink our fingers and thumbs like this and start pulling them apart. When you pull it apart like this, you've got a dot on the back of your right hand, you've got a dot on the back of your left hand, and you've got dots on each of your fingers and thumbs, so that's your 12 vertices. Now we can count triangles. You've got 5 triangles coming from the dot on the back of your right hand to the tips of each of your fingers, and you have 5 triangles coming out of the dots on your left hand to the fingers and your thumb on your left hand. See those 5 and 5 triangles? Now, in the middle, along the waist, you also have triangles going from the right hand with tips, points at each of the fingers and the thumb, and they're fitting in between, going to bases between 2 fingers on the left hand. You see those triangles that are pointing upward along the middle? Points on the right hand, bases on the left. You also have triangles with points on the left hand, fingers and thumbs, and bases on the right hand pointing downward in a waist. So how many triangles do I have with tips touching the right hand? How many with tips touching the left hand? How many triangles in the right hand? How many in the left hand? How many triangles does this thing have total?
What's that called?
It's got 5 here, 5 here, 5 pointing upward here, 5 pointing downward here. How many triangles does this thing have? That's 20. The non-meter stage function, you read it, take any vertex, and count around. Count how many triangles there are. 1. Just count around the vertex. Can you look up here? Well, here, I'll point it. Here, 1, 2, 3, 4, 5. This lines up to the hand. See, this is exactly the same shape. So this has 20 faces. Let's see if you can count the edges in a slightly more creative way. Count the edges. Each person has 2 hands, and each person has how many ends of an edge coming into their hand? You're saying 4. Let's look at it again. All right, so, sure. So you agree that each person has 5 ends of edges coming into their hand, and we have 12 hands altogether. So how many ends of edges do we have? 5 times 12, 60. So how many edges do we have? Wait, if you've got 60 ends of edges, how many ends does an edge have? It's a lot like tropical geometry. In tropical geometry, a line has 3 ends, but in this geometry, a line has 2 ends. An edge has 2 ends. We've got 60 ends of edges, so how many edges do we have? 30. 30. You agree with this? In the name of 20, Trump, I, and Pasta. In fact, now I said that we had 10 volunteers. We want to do things symmetrically. We've got a blue, green, red. So, you can grab the blue, green, and red. Hold up there. And there's another blue, green, red if you look from the other hand down there.
It's like we should do Christians rocket and
So, I need a volunteer over here. Blue, green, red. Blue, green, red. And down here and here and here. Carnage, squash. And another 4 volunteers. Here's green, blue, green, red. And blue, green, red. And wait, did I lose a volunteer? Well, it's a volunteer. When somebody want to come up? Volunteer opportunity.
I'm so angry right now.
We'll use blue, blue, red triangle. One hand, this one. Hold tight. What does each face look like here? How many sides does each face have? Each face is a pentagon. So, we've got 10 volunteers. How many hands? So how many vertices? So now let's count the number of edges. We have 10 volunteers, 2 hands each, so that's 20 hands. How many vertices come in, how many ends of edges come into this hand, sir? 3. How many into this one? So into each hand, we get 3 ends of edges. 3 ends of edges per hand times 20 hands. How many ends of edges?
60.
How many edges?
30.
And now you need to carefully count the faces. And in fact, your break dance problem here is, I claim that not only can we do this one, which, should I count it, or you want to count it? Would you count it? We've got a 12, got another 12. If you carefully look at this, you can build this during breaks. This is 12, it's called a dodecahedron. I claim that you can also make a hexahedron, a cube. The way to do that is you dismiss the original 6 volunteers. So the new 4 volunteers, hold on tight. The original 6, let go and you can go have snacks. Get in line for snacks. And
Let's fully the
back up and stretch your hands out. Long.
It's not a cube. What the hell are these?
So,
This is what has play.
oh, we did cube. And then if you think about this a little bit more, I'll let you puzzle. If you have the right number of people let go of the right hands, you can stretch this out and make it tetrahedron. So you can go from dodecahedron to the dodecahedron to the cube to the tetrahedron to snatch.
Yes, sir.
And on that note, why don't we meet back in here in about 10